almost finished chapter 12, the last chapter of material that we're going to be testing you on. We have another chapter on sustainability. It doesn't have as much, equations and calculations and things that we'll learn how to work through. It might be a little bit. This is pretty much the end of the material that we're going to cover this semester. So a couple notes in the days that are left. Today's Monday. We're going to finish chapter 12 today, and we'll introduce some of the basics of chapter 20, which is on sustainability. Wednesday, many people have told me they're going to be out of town for Thanksgiving. So I think what I'm going to do instead of lecturing that day to a half-filled class is I'm just going to hold a review. So it'll be like the final exam review. I don't have a midterm or the study guide written yet because I haven't written the final exam yet. Nevertheless, I will go over previous final exams, and you can bet it's going to look pretty similar, right? I do similar questions every year. I write new ones, but they're similar types. So on Wednesday, if you come to class, that's what we'll be doing. If you can't make it, they won't be for clicker points or anything, so up to you whether you come or not. I will record the lecture and post it like usual. Then Thanksgiving is Thursday, Friday. Monday, we will do the lecture on sustainability, right? Where it's going to be a debate lecture. Today, we're going to teach you the principles. On Monday, it'll be a debate format. It will be worth a number of clicker points, so you don't want to miss Monday, even though it's not going to be heavily on the final. Wednesday after that is the last day of class. You will make sure that you turn in your crystal final project the night before by 9 p.m. This microphone's working. By 9 p.m. you need to turn that in. And then in class you need to bring your crystal. We're going to weigh them and do the final voting in class. Okay? So we're almost at the end. Okay, so today what we didn't quite get to was the part of Santa with muscles that made me the most crazy. First off, that they pronounced piezoelectric was bad enough. But then that these crystals exploded was just ridiculous, right? So what are piezoelectric crystals? Are they at risk of exploding, right? Yes or no? That's definitely not the case. Piezoelectrics are an interesting class of materials because they make possible some really cool technology. How they work, they're a type of what we called a ferroelectric, right? Ferroelectricity, as the name suggests here, these are dielectric materials that exhibit a spontaneous polarization moment, right? So when you heat them up, there is no net polarization of these molecules. But when you cool them down, there exists a temperature, we call it the Curie temperature, as in Madame Curie, right? You cool below that temperature, and they spontaneously order, and you get polarization. So what does this mean? Well, if you remember from the last classes, we talked about sources of polarization. We said there was three main things that you could consider. In blue up top there, that represented electronic polarization, meaning the atoms themselves can be polarized. The atoms can slightly shift, the neutron can shift one way, the electrons can shift the other. That will produce electronic polarization, okay? It's not very big. Then the next one was ionic, right? Or, we call this ionic orientation. Ionic polarization, where you had a normal crystal here, and then when you apply an electric field, the positive and negative charged cations and anions are going to shift a little bit in response to this electric field, right? So if the atoms shift a little bit, that can give you a polarization. And then the last one was orientation, okay? Where the molecules themselves can rotate relative to the field. So when I say that you cool something down and all of a sudden it polarizes, what I mean to say is that you cool it down and at high temperatures it looks like this. It's random, and just by cooling it down, no electric field required, it moves and it does something like this, right? Why on earth would that happen, right? Energy is the reason, right? It's either entropy or enthalpy driving that. Now, for this scenario, I don't know of anything that does this spontaneously, where the spontaneous thing is rotational or orientational, right? I'm not sure of that one, but this one up above it is much more common. That a crystal is nice and uniform like this at high temperatures, but you cool it down and the ions shift. They do something like that, okay? That's what happens in these titanates. If you remember last time, the last thing we sort of said was the dielectric constant of materials was pretty low for a very long time. So polymers was like 4, maybe less. Ceramics could be typically like 3 to 10. Metals were conductors, so they don't have a dielectric constant because they conduct electricity. But all of a sudden, we discovered these materials, these titanates, that can get 4 orders of magnitude larger polarization, right? Their dielectric constant is massive. So how do they do it? They do it by moving atoms. So here's what a typical titanate looks like. It's our old friend, the perovskite, right? At high temperatures, in this case, for barium titanate, you've got A, B, O3. This is your A atom, B atom, O3. A is always the larger one. Barium is much larger than titanium, especially because if you look at the charges on this, what's going to be the charge of barium and titanium? Well, we can pull up the periodic table, and we can look where barium and titanium are. Barium is over here. Where is it? Where's barium? Over here. It's group 2, so it's going to be +2, almost for sure. Everything in that column is +2. Whereas titanium has 1, 2 in this column, so it could lose 2 of its d electrons, or 2 of its d electrons and 2 of its s electrons. And that's what happens. Titanium is very commonly 4+. So if you do the math on this, you've got 2+ and 4+. That's a +6. That cancels out with the -6 coming from your oxygen. So it works. It works for a perovskite structure. Barium is massive. You saw how low it was on the periodic table. It's clear down here. That's a much bigger ion. If we look at barium 2+ in its coordination number and 12 in the perovskite, its size is 1.61 angstroms. It's big. That's bigger than an oxygen. That's really big. Whereas titanium is going to be 4+ in a 6-coordinate environment. It's going to be 0.6. So a third of the size, basically. Much, much smaller. Okay? So they're not drawn to scale here necessarily, right? It's kind of close. These things should be a little bigger. These things should all be touching, right? But this is the perovskite crystal structure. Titanium, the small one's in the middle. These guys are at the corners, surrounded by 12. This one's surrounded by 6. The rest are oxygens. Everybody remember the perovskite crystal structure? Any questions I can answer about it? Okay. What happens is that at high temperatures, it is the perfect perovskite structure, meaning these atoms are centered exactly where they should be. If this guy's in the center of the unit cell, it's centered exactly in the center of the unit cell. These ones at the corner are actually centered right on the corners. But something curious happens. When you cool this thing down below 120 degrees Celsius, these atoms spontaneously shift. Okay? They shift and they do this. These A cations on the corners go up a little bit. They're going to shift up a hair. The oxygens are going to shift down. I don't know if you can see that, but it's actually shifted down. It's no longer centered on the atom, on the edge center, the face center here. And this titanium is going to shift up. Okay? Why does this happen? This happens because titanium is really small. And it's been put, because these atoms are so big on the corners, it makes a really big cage for the titanium to occupy. If the cage is larger than the titanium cation, and it is, then the titanium cation can actually shift around a little bit. It's in a cage that's too big for it, so it could rattle to the top side, it could rattle to the bottom side. It has the ability to basically move. And in doing so, it lowers its energy. So this is in a lower energy at low temperatures than this. Therefore, this turns into that when you cool it down. Okay? Any questions? Yeah, Abby? Well, so remember how we drew it like before? The cage looked something like that, and we said that the cation would ideally like to sit right in the middle of that cage and be touching all the anions around it, or as close as it can be to them. But if it's way too small, then you have this scenario, where it could sit there, or it could sit there, or it could sit on the corners, right? It has options, or in and out of the page. And that's kind of what's happening. Titanium's so small that it can pick different spots in the cage, and some turn out to be lower energy than others. Yeah, Abby? Oh, okay. So because titanium's so small, it can occupy different sites, and at lower temperatures, those sites become more favorable than sitting directly in the center. It could also sit right in the center. That turns out to be less energy, right? Or, sorry, more energy. It's a larger energy penalty. Okay, Sam?
So that polarization will propagate across the material?
So that's a great question. If your whole material, like if we drew our entire material, it's got grains, right, running all the way through it, and each one of these represent crystalline regions where maybe that's the way that the crystalline lattice is arranged here. Over here, maybe it's oriented slightly differently. Your question is, okay, you're going to cool it down, and we know that there's going to be a shift at low temperatures where your atoms are going to shift in one direction. So in this first region, let's say that they shift, the titanium is going to shift up. I'm just going to draw the titanium arrow, right? It's shifting that way. In some region of space, which may or may not be the same as the grain boundary, it's what we call a domain. Within this domain, all of the titaniums are going to shift the same direction. But in the same grain, you can have multiple domains. We talked about this in chapter 5, I think, 4, right? Where you can have things other than grain boundaries. They all have the same crystallographic orientation, but over here, maybe your titaniums all shift down, right? Do you see that these can be the same crystallographic orientation, but there can be titanium shifted up over here and down over there? So for example, this region of desks are basically a cubic lattice-ish, and it's basically all oriented the same way. But people on this side of the room, raise your hands up, right? Over here, you guys could point your hand down, right? And there's some sort of boundary between that. That would be one grain can have multiple domains. It could be more than 2. It could be many, right? That's what a domain is. A domain has to do with electronics or magnetics typically, right? So it's a polarization. It can be a magnetic domain, right? Where that could represent a spin magnetic field up, whereas down could be over here, and that's how you get your magnet out of this thing. It could be strain, right? If this is a piezoelectric, we'll get to that in a minute, but instead of a shifted atom, it could be a strain in your lattice, right? And that could be different in different regions. Are there any questions about the difference between a domain and a grain boundary? Or Sam, other question?
I just have another question, which is if you were to maintain a field while you pass the Curie temperature, could you force the domain to go in the same direction?
Yes. Yes, that's called poling. That's how you make these things better piezoelectric. So for now, realize that there's different grains in your material. The grains represent the crystallographic orientation. Within the grains, you can have domains, and they can be broken up as small or as big as you want, right? Where that's going to be different, in this case, polarization, okay? So for example, they've shown you here, this is the cubic lattice. The titanium could shift up, or it could shift down. These things are sort of reversed from one another, okay? Now, in order for this to happen, to go from this high temperature structure to the low temperature structure, you change symmetry. You technically change the symmetry because this z-axis here, the c-axis I guess we've been calling it, it gets a little bit longer at low temperatures. The whole thing gets a little bit taller, right? So now this length here is taller than these two sides. So A is equal to A is not equal to B. Because of that, it's no longer cubic. It's tetragonal, okay? So there's a change in symmetry. It goes from cubic to tetragonal, and it happens spontaneously. Sam's question was a really good one. He said, okay, it's at these high temperatures. If I apply an electric field to it, I can cause these atoms to shift, right? Atoms will do that. We showed that previously. A material that was nice and cubic before, this thing will turn into that if I apply an electric field. So I'm prematurely moving all of the atoms. If I release that electric field, they're just going to go back to the way they were, right? But if you leave that field applied while you cool it down, that's called poling, right? You induce poles in a certain direction. And that's how you make the most effective piezoelectric or ferroelectric crystals in general, okay? Any questions on that? Yeah, Jaden?
I don't really catch how combining the field and the change in temperature would make it effective.
Oh, okay. So imagine like that up and down hands example for a minute. It takes some amount of energy, let's say, to move your hand from up here to down here. That costs some unit of energy. So if your hand is already pointing up because I applied an electric field and pointed everybody's hands up, and then I took away all your energy, right, by cooling you down while that field is still in place, once you're down at low temperature, you don't have the thermal energy to switch, to move the ions to the down position, for example. So it'll just stay where you left it. That's called poling. Make sense?
Yeah.
Can I answer any other questions about this? We haven't yet said what these are useful for. They turn out to be super duper useful. We're going to show that in a minute. Any questions though so far on how you can create a polarization and it stays there by shifting atoms? So why is this so good? Why do you get 4 orders of magnitude better performance in these titanates when they were discovered? A couple reasons. First off, look at all the atoms that shift. I've got it sort of zoomed in here. Here's an example of some real numbers. Okay? You've got A, oxygen, and B, right? So barium, oxygen, and titanium, for example. This titanium is shifted up 0.006 nanometers from its center position. But remember, titanium is a 4+ cation. It has 4 electron charges, and you've shifted all 4 of those up. And then you've got your oxygens. They're all shifted down. There's 2 of them. So you've got 2 electrons for each one of these oxygens, and they're all shifted. These ones are shifted down by 0.009. These ones are shifted up or down by 0.006. So there's lots and lots of atoms overall that are shifting, and they all have a charge with them. Okay? So we could calculate the overall polarization. To calculate it, you just have to sum up the individual polarization from each individual atom. How do you calculate a polarization? A polarization is equal to a charge times a distance, right? How far do you separate the charge, right? Redraw that D, right? So our polarization for the atom, or for the crystal structure, I should say, is we're going to sum up each one of the charges associated with an atom and the separation distance associated with it. So we could go atom by atom through this. We could do the barium first, then the oxygen, and then the titanium. We could add it up, okay? So let's do this. In this one, the way that they've drawn it, the barium has not moved. It's still at the corners of the unit cell, okay? So if we start with barium, we would say that, what's the charge of a barium? It's a 2+ cation, so we'll do positive 2. And then we're going to multiply it by the distance that it's been shifted. And they've drawn it so that it hasn't been shifted. So it's just 0 nanometers. Okay? So we're not going to get anything from barium. Now let's do the next one, which is going to be, say, oxygen. And let's do the oxygens on the sides, and then we'll do the oxygens on the top and bottom. So the oxygens on the sides, they are -2. That's their charge. How many of them are there per unit cell? Well, there's front and back, side and side, and each of those are half. So there's 4 divided by 2. There's 2 atoms that are doing that. Okay, times 2. And then we've got how far it's shifted, which in these ones it's going down 0.006 nanometers. So I'm going to put negative 0.006 nanometers. Okay? Now we're going to add up our next one. Notice I'm always doing adding. I'm not changing the sign here. I'm going to change the sign based off of the charge, but I'm just adding these things up. It's just a summation. The last one is titanium. It's a positive 4 charge. There's 1 of them per unit cell. And it's shifted up by 0.006, positive 0.006 nanometers. We're forgetting one more. We forgot to consider the oxygens there at the top and bottom. Those are also 2-. So that's a -2. There's 1 of them per unit cell, right? 1 on the top and bottom, half in, half out, on average. And these things are shifted down by -0.009. So what I've not included here is I should include the fundamental charge for each one of these. Each one of these charges, we should multiply by their fundamental charge, right? 2 times the charge of an electron, -2 times the charge of an electron, 4 and -2. If you add those up, you'll end up with something in the units of polarization. Can I answer any questions about this? You just literally go atom by atom and you see how much they've shifted. The reason why these turn out to be such amazing materials, first off, titanium's 4+, so it takes a lot of charge with it. And second off, it's such a tiny atom that it can typically move a lot, whereas other materials can't move as much. Other materials that make really good dielectrics are very similar. Zirconates turn out to be really good because zirconium's right below titanium. It also can be 4+. You can put it with something like lanthanum, a really big rare earth. Lanthanum zirconate's going to have a high dielectric constant. It's going to be able to shift quite a lot. Any questions about this, about the mechanism of polarization in these materials? And again, because it's such a higher dielectric constant, that means that we can make way, way, way smaller capacitors, which allows us to miniaturize all the electronics that we care about, because capacitors are one of the basic building blocks. Okay? Any questions? Nothing? Okay, we'll keep going. The unit cell parameters do change as it goes from cubic to tetragonal. You can literally observe a change in X-ray diffraction. Right? Normally in X-ray diffraction, we would say that this peak, let's say, that the 100 peak would be the same as the 001 for cubic. Right? Those are the same for cubic. In other words, if we plotted the intensity versus 2 theta, we would see 1 peak corresponding to the 100 family. That's directions. Family of planes is curly brackets. Right? They would all be in the same family, so we would only see 1 peak. But when you cool this thing down, what are you going to see to that peak? Now the 100 will no longer be equivalent to the 001. Because, how did we calculate 100? For cubic, it was 1 over the d spacing. D was a function of HKL, where that equaled h squared plus k squared plus L squared all over A squared. But for tetragonal, it's different. How's it different? Now you've got 1 over d squared, where that's a function of HKL. Well, that's equal to h squared plus k squared. That's a bad 2. All these 2s are bad. Over a squared plus L squared over C squared. So if C and A are the same number, then these collapse to the same thing. But if C is different, C is now 4.03 instead of 3.98, even though you plug in 001 here and 100 there, you get different numbers because C is different than A. So you're going to get another peak. The question is, does it appear to the left or the right of that peak? If this here represents cubic, where all the lattice parameters are 3.98, when this thing shifts and one of the lattice parameters gets longer, we're going to get a shoulder on this or a new peak next to it. Does it go to the left or the right? Well, we think to the left. Let's make sure that's right. To check it, we would say that Bragg's law says lambda equals 2d sine of theta. Lambda is not changing. That's a constant. So sine of theta, we want to figure out if it's larger or smaller. So is d larger or smaller? Well, if this is a larger number, then d also got larger. This was in the denominator. This is in the denominator. So d, the interplanar spacing got larger for 0, 0, 1. Right? So d 0, 0, 1 is going to be larger than d 1, 0, 0. Everybody remembering this? We're bringing back traumatic moments from X-ray diffraction. Right? Any questions so far on this realization that D001 will be larger than D100 for the tetragonal phase? For cubic, they're equal. Abby? Yep. So, okay, so if we looked back at our diffractometer, the way that diffractometers are built, you've got your sample sitting here, and you bring in X-rays, and then your X-rays bounce out. So you've got a source, and you've got a detector. These are located at angles theta from one another, and you change that angle. You start out at a low angle typically, you start scanning it, and you go to high angles. And all through that period, you're measuring how many of your photons get back to your detector. You're bringing X-rays in, how many of them disappear due to destructive interference, and how many of them actually bounce through. And as a function of theta, or 2 theta is how we typically do it, you'll see that there are peaks, right? There are spots where they start to appear or disappear, right? And those correspond to interplanar spacings in your material. So I is the intensity of the beam that goes into your material and makes it back out. I is intensity. Okay, yep, tetragonal.
Is the intensity going to change between those two?
Let's ignore intensity for now. That's a different class. When you guys take characterization of materials, if you guys so choose to do so, you'll learn how intensity comes into this. It's nasty. We're not going to do it in this class. It's just kind of gross. Right now, we just want position. I'm just talking about position. And what we know is that since you have now 2 different values of d-spacing, then you have 2 unique solutions to Bragg's law, right? The same wavelength. If you have 2 different d values, then you should have 2 different observed peaks at 2 different theta values. So the question is it to the left or the right? Well, we know that the new peak, D001, is larger than the previous one, right? So if this value gets larger, this is a constant, this has to get smaller. And since it's the sine function, it's going to happen to the left. It's also going to get smaller. So we would see this new peak right there. As you cool this material down from above its Curie temperature to below its Curie temperature, if you look at X-ray diffraction during that process, you'll see peak splitting. I'll bet we can find an image of it. XRD, Curie temperature, peak split. Let's see what we find. Come on, internet. Don't let me down. Let's see if we see a good one. So maybe, yeah, right here. Here's a good one. So the cubic phase is in the dotted line. It's just one peak, right? In this case, two things happened. First off, the 0, 0, 2, that's the z-axis where it got longer, that shifted to the left just like we predicted. But in this material, the others actually contract a little bit. The other sides didn't stay the same. It wasn't like it just got longer. The other sides contracted a little bit for conservation of volume. That makes more sense. Most materials have volume conserved. If it's not just like atoms just get longer in one direction. They probably get longer and they shrink in the transverse directions. That's why the other ones are shifted a little bit to the right, because they got a little bit smaller. Can I answer any questions about this? This is typical fodder for a final exam question. Could you have worked through this? Could you do it now, having seen this? Maybe? Just general terror from the audience? All right, well, we can go over examples of this on Wednesday, I guess. Okay? So we've talked about the Curie temperature, written as T sub C, the Curie temperature. We've already talked about domains, that the domain doesn't have to be the same size as the grain boundary. It can be. It can be subsections of the grain boundary, though. Or not the grain boundary, the grain, excuse me. Smaller than the grain boundaries between the grains. I'm sorry, I'm saying that wrong. We've talked about poling to make this more efficient. In the most efficient piezoelectric, all of your material would all be pointing the same direction. So you can't do that great if you have a polycrystalline material, because if you try, let's say we apply an electric field to this thing, right? I'm going to apply an electric field this way. So positive side of the electric field is that way, right? So at high temperatures, all of my domains are going to do their best to line up to this field. But this thing's like diagonal. So these things, they can either go like that or maybe down like that, but they can't just point at any arbitrary direction. Magnetic fields can typically point to any arbitrary direction, but polarization cannot. So what it's going to do is it's going to depend. Like this one, the best it can do is maybe point like that, right? And if your material happens to be lined up exactly this way, then great, you can line it up. But the point is, polycrystalline materials are not ideal for piezoelectrics, because there's some degree to where like the symmetry of the crystal limits the way that it can line up to the field, right? So the best case scenario is you grow a big single crystal of this stuff, okay? That's how you're going to get the best orientation. So they grow single crystals, and then they pole them so that all the domains are aligned, and that's how you get the very best. Now, what are these things actually good for? It's all fine and well, like you can kind of shake your head and be like, all right, there's this thing. What do we use them for? Anybody do the reading? What do we use piezoelectrics for? Watches? Where? Quartz. A quartz oscillator in your watch keeps time, right? How does that work? Okay, you do. You apply, so let's take this material here. We're going to put leads on the top and on the bottom of this. So here you've got a battery, right? Connected to this thing, which is going to cause a positive and a negative side to this thing. If you alternate that, what you're doing is you're telling the atoms to shift from one side to the other, right? You can literally cause this crystal to change its shape, right? As you keep on alternating the current in this thing. So this is the phenomenon known as piezoelectricity. When the strain of the crystal, so that's piezoelastic, right? It would be a piezoelastic response. When the strain of the crystal, meaning the crystal changes shape in response to an applied voltage, that's the whole class of, whenever you have coupling of two different phenomena, we call these multiferroics. So if I applied a voltage difference that alternates, and in response I get strain, that's a piezoelectric. But if I apply a voltage and the response is that it changes the magnetic field, that would be a different type of multiferroic, right? So if you look at all the different type of multiferroic coupling, it gives rise to some really weird devices you could make. Multiferroics. So you typically see something like this. Okay, so here's our plot, okay? You can have, on the top axis, this is E, and then this is H, and stress. So E represents an electric field. H represents a magnetic field. Stress is just a stress, okay? So if you apply typically an electric field, you induce a polarization. Almost every material will do this. So that's not a multiferroic. But if you apply an electric field and you induce a strain, which you normally get from applying a stress, that is a piezoelectric response, right? But there's other ones, right? You can go from a electric field and it produces a magnetic moment. That would be a magnetoelectric, right? A magnetoelectric. You could take a strain, so you're going to, a stress, you're going to squeeze your material. If you produce a polarization, that's piezoelectric. If you produce a magnetic field, that's magnetoelastics. You can start doing some really cool devices. You can take materials where, we're not even showing temperature here, but they can make fridges out of magnetoelectrics, where you apply an oscillating electric field, and due to the changes in magnetism and the energy involved there, you can create refrigerators that don't have any fluid moving in them, right? You can do really cool things because of this coupling of what are normally very different responses. We normally think stress, strain, electric field, polarization, magnetic field, magnetization, but these things can be coupled. Now, the holy grail would be a material that couples all these things, or even couples any of them really well. And those don't really exist. There's some that work, like the titanates are a great example. They're really great piezoelectric multiferroics. We'd love to find some other ones, like magnetoelectrics. I did my whole postdoc on that, and they just don't exist. They're really bad. The best ones out there, instead, are two other things coupled together. It's a magnetoelectric coupled with a piezoelectric. So when you apply the piezoelectric field, it squeezes the material. That material squeezes its neighbor because it changed shape, and that material is a magnetoelastic, excuse me, and so that causes your magnetic field. The point is, you can make cool devices. The things that we do with them, you can make a watch that oscillates at a very specific frequency, where literally it's shaking in there because of the current that you're switching on it. What else can you do with these things? We're on time. What else can we do? Yes, Sam. This is the basis of most microphones, actually, right? So think about it. Piezoelectric pickups on your guitar or on a microphone, when you strum the strings of your guitar, you've got vibrations, right? As you vibrate that crystal, it's going to produce a tiny little, if it's a piezoelectric, you're straining it. Those pressure waves are going to cause it to shrink, contract, shrink, contract. You can turn those into electric signal via the piezoelectric response. You can then send those into an amplifier, and you can make awesome music, right? Hopefully. Okay? What else? Pramit, Faraz. Barbecue lighters take advantage of this. A barbecue lighter, those things are piezoelectrics. You squeeze on them, and then when it hits a certain point, it whacks it. So you elastically deform it quickly, and so it's going to produce a large voltage between two electrodes that sparks. That polarization can be used to create a spark, and that starts your barbecue. Or at your home, your stove has the same thing. So I hand over here, was it Isaac or next to Isaac? Oh, same thing?
I think I read a few years ago that they found a piezoelectric that they wanted to put in pacemakers. So as the heart pumps,
okay,
generate electric charge that would then
yeah. These are really interesting energy harvesting modules you can make out of them. Like, for example, I've seen subway stations where they're demonstration units. They're not super practical yet. But when you walk across the floor, every time I step on the floor, I'm compressing it, and then I let it off, so I'm uncompressing it. Each time that cycle happens of me squeezing it, I'm producing a polarization in a piezoelectric material. If I harvest that charge and store it somewhere, then every time a bunch of people step on something, you're generating power. The same thing can be done in your heart. Your heart it could be the strain from your heart beating could produce a small voltage to basically keep your heart running, right? If a pacemaker needs that tiny little current to keep it going. So all sorts of crazy devices that sounds just like science fiction are made possible because of these interesting coupling. Anybody else know another one they want to mention? There's lots more that we could think of. Like, yeah, Josh. High precision scale? Do they use piezoelectrics? Okay, so the strain you produce, you turn that into an electric signal, and you can turn that into a mass, you mean? Is that how they all work? That might be how they work. I don't know that. It might be. Now, we've all been going one way. We've been starting with a stress and producing the electric polarization, the electric field, right? But we can go the other way. You can apply an electric field, and you can induce a stress, right? So ultrasound is a good example of this. When you look, like my wife's pregnant right now, and we can look at our little baby's face. The way we can do that, and it's amazing, we've got a piezoelectric crystal. I take an alternating signal on this crystal inside the ultrasound head. That produces a vibration. This thing vibrates a little bit at a specific frequency. That goes into the belly. It bonks off the baby's head. It bounces back, and you've got a separate crystal which takes pressure waves coming in. That pressure wave causes a displacement of atoms. It turns that into an electric signal. You can go back the same way. You can start doing tons of things with this. Abby?
Sorry, I think I'm just getting really lost based on all of these examples and having a really hard time visualizing.
Okay, let's show a picture of it, right? Let's say I take right here, right? Here's an example of one. You've got a piezoelectric crystal, right? As you squeeze on this thing, the polarization changes, right?
That would be like the perovskite, where you said the titanium went up and down. Is that what you mean?
Kind of. What happens in the perovskites, the piezoelectric, is the following. You've got a tetragonal crystal. I'm going to draw it really exaggerated, right? That's our tetragonal crystal. So the polarization spontaneously might be positive is side over here, and negative side is over there. Okay? Now let's say you squeeze on this thing. What's going to happen? It's going to deform and become like this. And again, I'm really exaggerating this, right? So now you're going to have positive and negative that way. Right? So if you squeeze on it, it becomes that. It changes its orientation. And then if I squeeze on it this way, it goes back to that way. It's reversible because of this being a piezoelectric material, multiferroic. So if you alternate your current many times back and forth, it's going to be switching between these states, and that's a strain. So it's going to be vibrating. Your crystal will literally be vibrating. They use these for tiny actuators. So if you need to move components with tiny little motors, you can only gear things down so small. If you need to move things atomic distances, they use piezoelectric actuators, right, to move them tiny, tiny distances. Jared? To feel vibrations from engine knocking? I don't know that. It wouldn't surprise me. I don't know that. Tiny vibrations, physical vibrations, they turn into sound. That might be the case. I don't know that. There's a gazillion and one really cool applications for this, but it all relied on a material that produces a large polarization. If we were still using clay, to do these things, we wouldn't be able to do any of the cool devices. You would not have ultrasound like we have it today. No way, right? We can do cool things now because of this. Can I answer other questions about this? There's other courses you can take that go into greater detail. For example, Introduction to Ceramics in our department. You go into much greater detail in these and learn more about it if you're interested. Pramit? Of a type of material? Barium titanate. Lead, PZT is another one. Lead zirconium oxide, or sometimes they call it zirconium titanate. Sometimes they mix the two. Those are really high dielectric materials. Quartz is one. There's quite a few materials out there. The key is that the atoms have to be able to shift. So if it's a super close packed lattice where there's no room for them to shift, it's probably not going to be a good dielectric or good piezoelectric. Okay? Yeah?
So is piezoelectricity, is that both force causing polarization and electric field causing force?
Yeah, that's right. Piezoelectric is the phenomenon whereby you get coupling between a strain, polarization, stress, and electric field. Those phenomena are coupled if it's a piezoelectric, right? Now there's something else, like we could make this a four-dimensional triangle if we wanted. We could add temperature. And there's something like, for example, a pyroelectric. So pyroelectric. Pyro means change in temperature. Kind of sounds like a pyro, like heat is involved. So as you heat a crystal up, right, it changes dimensions. It's going to either shrink or contract. If it changes dimensions, that might also shift ions. So it might produce a polarization just via temperature change. So I think Sam might have asked about this a couple classes ago. A pyroelectric, we're not showing temperature here, but you could also include temperature in this multiferroic coupling. So it's complicated is the answer here, but it allows us to make really cool devices, okay? Like magnetic dilution fridges, right? Or guitar pickups, or all these things are possible because they bring together phenomena that you wouldn't expect to work. And like I said, you would love one material like PZT that can do this on its own, but for some of these phenomena, you don't have that. So instead what they do is they take a material, which is two different phases. So I'll draw this like this, where you've got phase A and you've got phase B, right? And they're just put together in some random order. Let's say that we apply an electric field to this, so positive and negative. That might cause this phase to expand a little bit. So it's the piezoelectric, okay? It expands. But think about the phase in between it. This phase is getting squeezed a little bit. If that material is a material that normally has a stress to magnetic field, a magnetoelastic material, right? A magnetoelastic material, this would produce a change in the magnetic field in these directions. So by having two different materials that are two different types of ferroelectrics, like this is your actual ferroelectric, this is your magnetoelastic, by putting them together, you can get an overall multiferroic device. That's typically how they do it right now, because we don't have one material that exhibits basically good coupling in between all these different phenomena that we care about. So instead, we put together two materials that have good couplings in one category, and then the strain that happens as they squeeze on one another, that's the coupling. It's called a second-order coupling. This is way more than I wanted to say about this. I just wanted to get the main idea that piezoelectrics are awesome. It requires a fundamental understanding of crystal structure on how they give rise to their properties. So we didn't save very much time for sustainability, which I'm not proud of. But we will spend a whole day on it a week from today. So let me just say right now a few words about sustainability. I don't think that we as engineers give it nearly enough credit. When you go out and get jobs, your boss, he or she's going to say, make me the best device, the cheapest possible. Or in other words, you're going to design for the bottom line, right? The bottom line being cost. There's this idea in sustainability that you can't just think about cost. You have to consider what they sometimes call the triple bottom line, where you're looking at cost, but you're also looking at what else? What else matters? What else matters other than cost? Is it just cost is king and we do anything we want and then cost is the only thing we care about? Jared? Tell us what that is.
Well, you have to look at the social impact, the economic impact, and ecological.
There it is, right? Economic, that's our cost. That's the one bottom line. You've got socio, like the impact on society, the sociological impact, and ecological. What does that mean?
And then there's also a better scale of sustainability between cleaner and cleaner.
Yeah, so you're right. Because there's not just like positive or negative. There's scales to these, right? It's way more positive or way more negative. And balancing these things is tricky. Have you seen examples in any product that's been made lately where they try and strike a balance? Sustainability has become, thankfully, a popular thing right now. Now, I think corporations are being a little bit cheesy with it, but Jared?
Batteries, if you look, they use the least amount of cobalt in any other company.
Why is that an issue? We're actually going to do a lot of reading on this. Cobalt comes from the Democratic Republic of Congo, almost 100%, and it's a lot of children mining, and it's a lot of very unsafe conditions. There's a lot of environmental impact. You can see like these things are all tied together. The price of cobalt is great. We want it to be as low as possible, but not if it means little kids are like dying in mines, I hope, right? So these things are all intertwined. And I'm not here to tell you there's like one easy way to design for materials, because there isn't. This is a really messy situation where you just have to be aware that these factors impact lots of different things, and that you try and quantify them to the best of your ability.
We really only get cobalt from Congo?
Like 90%. I can tell you the exact number. My grad student just wrote a paper on it. It's very, very high reliance. And that means we've had 2 Congo wars in my lifetime. And what did you think that did to the price of cobalt? It's not a good thing. It went way up. Plus Zambia, their neighbor, took all their cobalt. It was bad news. So these things, most engineers, we don't think about it. We just assume that alpha Azar or sigma Aldrich is always going to have whatever material I want. I'm going to be able to order up whatever grade of aluminum or steel or titanium or whatever plastic I want, and it will always be there. And we don't think about mostly the environment. We're starting to think about that. Where does sociology come in? The impact on society. We already talked about children mining. What is another impact on society of engineering decisions? Yeah.
Well, if we're constantly getting new products, we might be conditioned to want new products even when our current products aren't
Yeah.
good yet.
It really drives consumerism, which is good or bad. Depends, right? If in terms of an ecological impact, it's probably not great because we're putting more things in the dump at the current rate of recycling. Jared?
That's important because that's part of life cycle analysis. And life cycle analysis is the most important thing for ecological impact of the product.
Tell us what life cycle analysis is.
Life cycle analysis is you start at the inception of the product, so it's the getting materials all the way to ending the product. Like today we were looking at satellites, and you make the satellite, is the cost of the satellite up, the cost of running the satellite to fix anything you can't fix in the satellite, and then finally crash it into the water, or to have it burn up in the atmosphere. Available impacts. Those you can't upcycle because those have to be
Yeah. So there are many, I would say the vast majority, like 99% of products, are not designed for cradle-to-cradle utilization. Instead, we just accept the fact that we're going to throw things away and not use them again, right? So you're starting out with your raw materials. Let's move over here, raw materials, right? Which themselves come from ecological processes. We turn these into materials as engineers, plastics, steels, whatever. We manufacture them into products, right? So now you've got a product that has some useful lifetime. It's going to interact with the world in some way. We're going to consume it. If that gets used again perfectly, that's best case scenario. That is far, far from typical. It's much more common that we either landfill it and it doesn't get used at all. Hopefully, if it does get landfilled, then it decomposes and we can use it again. That's just not the case with much of what we're doing. So there's a gazillion more things we need to say about this. So on Monday, I'll probably say a few more keywords about this, like just defining things. And then we're going to have some debates on a few big issues where there's not an easy solution. We're going to talk about the electrification of vehicles. And we're going to talk about nuclear power. I've put 6 articles online. They're really short, easy to read, most of them. Take a look at those. We will have clicker questions to make sure you actually read them in class. And then we're going to debate these things on Monday. So on Wednesday, come for a review. On Monday, come for sustainability.